Okay, so let's continue where we left off previously. Uh, so we were looking at various techniques for dimensionality reduction. Right, so we've seen the Johnson-Linden-Strauss lemma, which was dimensionality reduction maintaining pairwise distances or approximately maintaining pairwise distances, and PCA, which was such that to dimensionality reduction techniques which minimizes the sum of the squared errors within the data set, and compressed sensing, where the goal is to compress a signal that is guaranteed to be sparse. All right. So concretely, the problem was to find a matrix A, a D by capital D matrix, such that we can recover any sparse vector, S sparse vector, exactly given these linear measurements AX. Right. So basically, you are given a vector which has at most S non-zero entries, and this is in dimension capital D. The question is it possible to take little d many linear measurements and still be able to recover X exactly? All right. And it turns out that it's possible, and in fact you can make little d to be some constant times little s times log d. All right. So I won't prove everything, but I'll give a sketch or an outline of how you can prove this. In fact, you've already seen much of the tools. It boils down to using some concentration inequalities, and there are a lot of elements of the proof that we use to prove the Johnson-Linden-Strauss lemma. In some sense, the ideas are very, very similar. All right, and also this S log D is in principle the best that you can do up to a universal multiplicative constant, because if you had to store S non-zero entries, then you would need at least S log D bits. All right, so that at least intuitively it feels that this should be information theoretically optimal. All right. Okay, so the main idea that is used to prove that this is indeed possible is this notion of the restricted isometry property. All right, so the big question is, how can we choose this matrix A such that this has this particular property? And for this, we'll look for matrices A which are almost an isometry, in the sense that you take any vector X, then or a sparse vector in this particular case, after taking the linear transformation, the norm of the vector doesn't change by too much. All right. So we'll say that the matrix A satisfies epsilon comma S RIP if for all non-zero X, which is S sparse, that is the L0 norm is less than or equal to S, we have that basically the norm of W times X is epsilon close to the norm of X, or in this case norm of, sorry, not W, A, norm of the L2 norm squared of A times X divided by L2 norm squared of X is less than or equal to epsilon. all right, or equivalently, this, right? So again, what we wanted in the case of the Johnson-Lindenstrauss lemma was very similar, right? Except that instead of looking at the norm of a times x, we were looking at the norm of the distance between, or the distance between x1, xi and xj, or in other words, the norm squared of a times xi minus xj. Right, so that was the idea behind. So the requirements in the RIP is also very similar to the requirements that we had for the Johnson-Lindenstrauss lemma, except there we had a finite set of vectors, whereas here we have an infinite set of vectors. We wanted an A such that given a set of n vectors, right, and this happens for all I comma j. All right, so in this case, if you recall the proof technique that was used, we essentially just used sub-Gaussian concentration. We took A to be a matrix with IID sub-Gaussian entries and showed that for any fixed pair xi comma xj, this holds true with very high probability. We derived an upper bound on the probability that this does not happen. And since there are the number of xi xj pairs that are given to us are just n choose 2, you just take a union bound over all pairs, and you got the and then we showed that the probability that this does not happen for all pairs I comma j, this is something that is vanishing in n. Right. In contrast, over here we could use something similar, except that there's a little bit of a problem. Here we want this to be true for all S sparse vectors, which are infinite in number. All right, so we can't just take a simple union bound over points, over vectors. All right. If we fixed one particular vector x, then and we chose A to be, let's say, a matrix with IID sub-Gaussian entries, then the probability that this does not happen for a fixed x, this will decay exponentially in the dimension. All right, but the problem where we get stuck is that you can't take a union bound over all possible S sparse vectors. But okay, so that aside, how does this help, all right? Because our requirement is that we want perfect recovery of x from a times x, correct? And this RIP only says that the norm is approximately preserved even after a linear transformation. So let's see the following statement. So let's fix any epsilon that is strictly less than 1, and suppose that A is an epsilon 2s RIP matrix. Okay, and let's say y is equal to a times x for any s sparse x. Okay, the thing to note is that x is S sparse and A is an epsilon 2s RIP matrix. Okay, the question now, what I want to say is that from y equal to A times x, it is possible to recover x exactly, uniquely. And there's also, this can also be solved using an optimization problem. So if, suppose that we have x tilde or min so let's say that we solve this optimization problem, right? The optimization problem is you minimize the L0 norm of V subject to the constraint that A times V is equal to Y. Okay, so you're looking for the vector with smallest sparsity, which is the same as what you see, all right, which has the same set of measurements as Y, right? Now there could be multiple vectors which come out as solutions to this optimization problem, all right? The solution may or may not be unique. Let's pick any such vector x tilde. Okay, the claim is that in fact this optimization problem has a unique solution, and it is exactly what we want. Okay, so right now I have not said what exactly the dimensions of A must be. All right, I have not told you how many measurements are required to be able to recover, or how many linear measurements are required in order to be able to recover any S sparse x from y is equal to A times x. But as long as I have a matrix A that satisfies epsilon 2s RIP, it is possible to uniquely recover x from A times x, and in fact that can be done by solving this optimization problem. Okay, so if we have a way of solving this optimization problem, then we can recover x uniquely. So let's see why this lemma is true. Okay, so suppose, for the sake of argument, let's assume that x tilde is not equal to x. We want to eventually arrive at a contradiction. Then x tilde minus x is 2s sparse. So X has at most S non-zero entries, all right, and since X tilde is obtained by minimizing the L0 norm such that A times B is equal to Y, the L0 norm of X tilde can be at most S, could potentially be less than S, but it can't exceed S because there is already a solution to A times B equal to Y, which is S sparse. So the minimum sparsity can only be lower, right? So X tilde minus X must be 2S sparse, all right, and we know that A times A is epsilon 2S RIP. So by definition of the RIP property, we have norm of A times X tilde minus X square divided by norm of X tilde minus X square minus 1. Let me perhaps write this in the other way. Okay, let me say that, yeah. A times X tilde minus X square divided by norm of X tilde minus X square minus 1 should be less than or equal to epsilon, right? Just by definition of the RIP property. Okay. But then what is A times X tilde minus X? What is A times X equal to? Y. What is A times X tilde equal to? Also equal to Y. So so A times X tilde minus X, this should be the zero vector, right? So this essentially becomes 0 minus 1 less than or equal to epsilon. But we've assumed that epsilon is something which is strictly less than 1, all right, which cannot happen. This is a contradiction. And hence X tilde should be equal to X. All right. A is some matrix. It's not a proper projection matrix. It's a fact matrix, right? It's not a square matrix. Remember that we want an A. So A is a little d by capital D matrix, where small d is much smaller than capital D. All right, and there are no other restrictions on A. It can take any. It doesn't have to be a orthonormal. It doesn't have to have orthonormal rows or columns. No restrictions whatsoever. Okay, so this means that we can recover x from a times x, right? So x is equal to arg min overall v equal to ev equal to y L0 norm of v. But unfortunately, there's no computationally efficient way of solving this optimization problem. The main reason is that the L0 norm is not a convex function. All right. So instead, we will want to obtain x through a different method. Instead of minimizing the L0 norm, we'll try to minimize the L1 norm. Okay, and hope that with that we'll be able to recover x. And in fact, yes, we will be able to recover x. So suppose that A is epsilon to s RIP with epsilon now smaller than 1 over 1 plus root 2. Then, as it turns out, x is equal to arg min overall v such that a times v equal to y of the L1 norm of v. So instead of doing an L0 minimization, you can replace that with an L1 minimization, and this is a convex optimization problem. And hence can be solved efficiently. I will not prove this, the proof is a little bit involved, but not too hard. You can just see the book by Shai Shalev Schwartz. For the proof. It takes a couple of pages to prove this. All right. This is assuming that you're able to obtain an RIP matrix. All right. So the question is, what is the smallest little d for which we can construct an epsilon 2s RIP matrix? So,
does it have any structure to it because of the epsilon?
no, nothing. It has nothing to do with the structure at all. It's just, so epsilon 2s will change the value of little d, the smallest little d that you can choose, such that you can get an epsilon 2s RIP matrix. So if d is some universal constant times s log d by delta epsilon divided by epsilon square.
How does like this S pass vector space look like?
It's not a vector space.
I mean, it's like unions of vector spaces.
Correct.
Like, I mean, if you have a one sparse vector in two dimensions, it's
Okay.
only the axis.
It'll only be the axis, yes. So it's not a convex set also, right?
So anything on those axes can be projected to one dimension.
Yes, correct. That's right. Well, we don't know whether it can be projected to one dimension or not. If you can construct an A, yes, you can project it down. Right. Okay. And A has IID Gaussian 0, 1 by D entries. Then with probability is epsilon S RIP with probability at least 1 minus delta. So, I mean, you've seen expressions of this form quite a bit already. So, it should hint that whenever you see something like something times log d by some delta epsilon divided by epsilon square, there should be some concentration inequality in the proof, and that's exactly what we do. So basically the idea is you fix an x which is S sparse, right, and then try to find an upper bound on the probability that A in fact the S sparse is not particularly important. So A norm AX minus norm x square greater than epsilon norm x square. So you get an upper bound using a standard concentration inequality. And the next step is again you can't directly now take a union bound because the set for which we want this to be true is an infinite set. So the next step is to use a covering argument. So in fact, instead of proving this statement, you prove a statement of the form this being greater than epsilon by 4 norm x square. Again, it doesn't change the technique, but now the covering argument is you show that there exists a finite set Q with the size of Q being, in this case, 3 by epsilon to the size of D, such that such that there is at least one, so given any x of unit norm, of norm less than or equal to 1, there is at least one point in Q that is at a distance of at most epsilon. Okay, so in this case, I think we wanted, let's just take epsilon by 4 so that this is some 12 by epsilon to the d.
What is the first less than equal to?
Which one? 12 by epsilon whole to the d.
No, not that. The first.
One second. You mean here? Oh, probability. It's upper bounded by something. I'm not giving you the exact form. But yeah, it's something that is exponential in d, exponentially decaying in d. And epsilon square. So it would be e to the minus some constant times d times epsilon square. Right. Sorry, there's a small mistake over here. This should have been capital D.
Carving argument is for L2 ball.
It's for the L2 ball. It doesn't really require sparsity.
The sparse vectors, you could do something better.
This is good enough. You can't really do anything much significantly better than this. Again, you can potentially improve the constants, but there's nothing, you don't get a significant improvement. Well, okay, so maybe you could get a slight improvement in terms of Q, but in the end, when you plug it back in here, you don't get any improvement in the small d that you can get. All right. And then you combine the covering argument. So first, you take a union bound over all possible points in Q. Okay, so basically the probability that this happens for even one vector in Q is upper bounded by whatever probability you have over here times 12 by epsilon whole to the power d. All right. But then if there is, for every point, for every point x, if there is at least one point v for which this distance is at most epsilon by 4, then again you can sort of massage it to, you can then take a union bound over this and something that involves this to show that eventually the probability that A times x minus norm x square is greater than epsilon norm x square for any s sparse x is less than or equal to something, whatever, the union bound. Some g of epsilon, delta, and capital T. As long as the right hand side is strictly less than 1, it means that there exists at least one A for which this happens, or this is not violated for any s sparse x. Okay. I know I just gave a very high level overview. There's a lot. I mean, compressed sensing is a whole field in itself, but this is just to give a flavor of what the problems in compressed sensing look like, and what are some of the most basic tools that are used. There's a whole area on analyzing algorithms for compressed sensing, getting more efficient algorithms and analyzing them, analyzing the runtime, their performance, and so on. All right, and this is in the case where you want to recover x exactly. Now, suppose that you're given there's a whole area, whole sub branch of compressed sensing where you're not really given y equal to a times x, but maybe what you have is y equal to a times x plus some small amount of noise. And the question is, how well can you recover x from noisy linear measurements? Any questions? So these are some different ways of doing dimensionality reduction and the kind of tools that you use to analyze dimensionality reduction. Okay. We'll now sort of switch gears and look at a bunch of other topics. Okay. And at least today I'd like to discuss what are called ensemble methods. So we'll again go back to the problem of binary classification with 0-1 loss. And we saw that ERM is a good learner. If the VC dimension is finite, then ERM is essentially the best that you can do, right? And if the VC dimension is infinite, then there's really not much hope, except perhaps you can, if you can express the hypothesis class as a union or as a countable union of hypothesis classes with finite VC dimension, then you can do structural risk minimization. But so far, the only techniques that we've seen, the algorithmic techniques that we've seen, are empirical risk minimization and structural risk minimization. But now, given a hypothesis class, uh, with, let's say, finite VC dimension, is there a way of efficiently doing something similar to empirical risk minimization? Because we've seen that empirical risk minimization can be computationally intensive, right? Even for simple hypothesis classes, we may not be able to solve the empirical risk minimization problem. Okay, so we'll see a completely different approach for doing training, so to speak. Okay, and for this we look at the special case where we want to learn a concept class. So let's say that we want to learn the concept class H, which means that whatever data that you observe, all of the points are labeled using some predictor from this concept class. All right, but you don't know what is the distribution of the data points. So for every distribution on the data points, we want to make sure that we want to design a learning algorithm that can give us arbitrarily small probability of error. Right? If we do empirical risk minimization, then we know that that's potentially solvable. But now we want to consider the case where doing ERM is computationally very intensive. Okay, so we can't do ERM. So is there a way of designing a learning algorithm such that eventually gives you a small training error? All right, so right now we'll only focus on designing an algorithm that can achieve arbitrarily small training error. We know that if we do ERM, then we can achieve zero training error. Right, so we can achieve Rs of H equal to 0. There is at least one H in the hypothesis class for which Rs of H is equal to 0. But we can't do this computationally efficiently. So we'll see a completely different approach where, although we know the concept class, we're not going to design a predictor that comes from this concept class. We're going to pick some other hypothesis class where it is easy to do training, but maybe it doesn't do so well. Okay. So in particular, we will first try to construct a hypothesis class for which you do something that is slightly better than a completely random case. All right. So we'll say that a learning algorithm we'll say that this is a gamma weak learner if for every delta greater than 0, there exists an n delta, some positive number n delta, such that if we have a data set of size at least n delta, then the probability that this learning algorithm outputs some hs hat which does slightly better than a completely random guess is at least 1 minus delta. So with probability at least 1 minus delta, this learning algorithm outputs a predictor that achieves a probability of error that is slightly less than half. So if you didn't have any training data at all, you could just guess the label randomly, and that would achieve a probability of error of half, right? But right now I want a probability of error. I want with probability at least 1 minus delta, the probability of error must be less than half, at most half minus delta. Okay? And the whole idea behind ensemble methods is to construct a bunch of weak learners and combine them somehow to give a strong learner. So a learner is said to be strong if you can make gamma to be arbitrarily large, arbitrarily close to half. All right. So a packed learner so we'll say that a pack learner is a strong learner. So we'll assume that somebody gives you a weak learner, and there's a computationally efficient way of getting this weak learner. If we are guaranteed this, then is it also possible to derive a strong learner computationally efficiently?
What's the difference in definition of
So again, if we are just looking at learning concept classes, then basically I would be able to make this arbitrarily small. Whereas this gamma weak learner is parameterized by gamma. So gamma could potentially be 0.01, and for a fixed, so I'm not guaranteed that I can make gamma arbitrarily close to half.
How do you get weak learners
In general, so there is no systematic approach of getting a weak learner. But for many problems of interest, it's easier to find a weak learner than it is to find a packed learning algorithm. All right?
Won't the same gamma be there for both
Which one?
weak learner and a strong pack?
So if it's a strong learner, it's also a weak learner. That is straightforward. But so the weak learner may never be able to achieve a gamma that is arbitrarily close to half. So when I say that there is a gamma weak learner, it only means that I can make this delta arbitrarily close to 0 by increasing the number of samples. But it's possible that no matter how many samples I'm given, I can never make gamma close to half. right? But there's some fixed gamma. It could be bounded away from half, but as long as gamma is positive, it could be 0.01, 0.001, that's okay. But I want this delta, I want to be able to drive this delta down to 0 as I let the number of samples tend to infinity. That's all. So the question is it possible to somehow combine whatever combine means, weak learners to give a strong learner? Right, so this is a question that was posed by Kearns and Valiant in, I think, 1988, and the answer was given by I think Shapire in 1990. So this was an approach that is now called boosting, but the algorithm given by Shapire was not efficient. It was not a it was just some theoretical result to show that yes, it is possible to combine weak learners to give a strong learner. But then that was improved later on by Shapire and Freund, and which is now called the Ada boost algorithm. So let's see what is boosting and specifically what the Ada boost algorithm is. So
Yeah, here is adaptive.
I'm sorry,
Ada here is adaptive.
it is adaptive. We'll get to what that is later. All right. But let me just set up the problem or the high level idea behind this idea of boosting. So the setup is that we're given a concept class H, all right, which means that we're given samples that are labeled using some function within this concept class. So there is some H which achieves zero empirical risk. Okay. But now we are not going to design these predictors from the concept class. We'll instead design a predictor using some other hypothesis class, which I'll call a base class. Okay. And this base hypothesis class is what I call a simple hypothesis class, such that I have two properties. One, I can do ERM very efficiently on this base hypothesis class. It doesn't necessarily have to be ERM, but there has to be some learning algorithm over which such that I can do over this base hypothesis class. But typically we look for hypothesis classes over which ERM can be done efficiently. But more importantly, for any concept, so suppose that all of the points are labeled using some h from the concept class h, there is some base predictor h, let me call it hb, that achieves error less than or equal to half minus gamma for all input distributions px. So essentially there is a computationally efficient weak learner over the hypothesis class B when the concept is coming from H. So just to maybe see a couple of examples of what a weak learner may look like.
So
Yep.
that's true for all PX, right?
All px. Because we're assuming that given x, y is labeled from according to h. Right? So it's not the agnostic pack learning framework that we're seeing here.
And what is the, can you just describe efficiently more than that?
There exists a polynomial time algorithm or an algorithm that you can compute in very small runtime.
Small means like
Whatever.
not exponential.
Definitely not exponential, but whatever you may desire. Maybe if you want a linear time algorithm, then fine, linear time algorithm. All right? Because in the end, the strong learner that you construct, the computational complexity of implementing the strong learner will depend on the computational complexity of learning the weak learner. If the weak learner takes exponential time, then you may as well just run ERM on H. There's nothing else to be done, right? So whatever your computational requirements are, this weak learner satisfies that. Okay. Fine. So this is basically saying that there is some base predictor that achieves an error of half minus gamma for every concept, and it's possible to do ERM efficiently on B. Another way of saying this is that for any H, there is a weak learning algorithm which outputs some HB from the base hypothesis class that achieves probability of error half minus gamma. Okay. So let's see a couple of examples. So suppose that my H is the set of all predictors over R that can be described using two thresholds. All right. And let's say that my base hypothesis class is the set of all h of x, which can be written as x greater than or equal to theta. So clearly B is a whatever simpler hypothesis class than H. And I claim that it satisfies the requirements that we have over here. For every H, there is, so in other words, for every alpha comma beta, there is some theta which achieves a probability of error less than or equal to, or which is strictly less than half. So even before we go to that, let's see what is the smallest error that we can potentially obtain using predictors in B. Suppose that this is the ground truth, right? Then you can see that if I, let's say I pick a predictor, pick a particular theta, this will have to make some error. All right? But how small can this error be? How? For every distribution. Why half?
Theta is equal to alpha. So half of them can be classified correctly.
Not necessarily, right? Because whenever, so I'm free to choose theta, right? I've just illustrated this particular theta, but by choosing theta, how small can you make the probability of error? Why?
I think it's
So
basically
let's,
the probability of x happening between alpha and beta and after beta.
correct. So let's maybe, let's assume that x always lies in the interval from 0 to 1, just so that the region over which we're classifying is bounded. Okay. And let's pick some arbitrary alpha comma beta between 0 to 1. Okay. Px could be arbitrary. Okay. But alpha and beta are fixed. All right. You're free to choose theta based on Px and also alpha comma beta. theta you say would be either alpha or beta. Okay. Okay, when would you, why would you choose theta to be equal to beta?
The theta would be alpha or 1.
Okay, yeah. So really, if you think about it, uh, if theta is equal to, let's say, alpha, okay, then if it means that you're getting everything right in this region and in this region, but then you're getting everything wrong in this region, right? If you choose theta to be equal to 1, then you are getting everything right in this region and this region, but everything wrong in this particular region. So let's say I choose theta equal to alpha, then probability HB is not equal to H. Let me call this region I1, this region I2, and I3. So this is the probability that X is in I3. Right? And if I choose theta is equal to 1, then the probability that HB of X is not equal to H of X is the probability that X is in I2. Okay. So how small can the probability of error be? So the claim is that if probability X in I3 is less than probability that X is in I2, then you select theta equal to alpha, else suppose this is my strategy of choosing theta. So across beta and alpha, how large can the probability of error be? So therefore, probability of error is min of probability that X is in I2, X is in I3. If alpha is 0 and beta is 1, correct, but that's the best case scenario. I mean, it's one of the best case scenarios. What is the worst case scenario? So I want to know how large can the probability of error be?
At most half.
At most half. when is it exactly equal to half?
0 half.
0, half and half, correct. So it's basically when exactly half of the probability is here and half of the probability is here, right? But let's suppose that sure. So let's suppose that I make one more tweak. Let me add the following collection of functions, x less than or equal to theta as well. Okay. Now my strategy is going to be, so my HB is going to be indicator x greater than or equal to alpha, indicator x less than or equal to beta, indicator x greater than or equal to 1, or indicator x less than or equal to 0. Let me define P1 to be the probability that, or Pi to be the probability that x is in the ith subinterval. So what is the probability of error of this particular classifier? The first one.
That is when the minimum is I3.
Sure, I mean, let's not worry about which one is the smallest, but what is the probability of error for this classifier?
Probability of
So this is the probability of error is, the probability of error is basically P3, probability of I3. What is the probability of error of this particular classifier? I1. What is the probability of error of this classifier? I don't think I really need this, but yeah, what is the probability of error of this classifier?
should not be the other way.
Which one?
Either x greater than
Okay, I think yeah, in these cases I get the same classifier, so it's fine. I don't think I need this at all. Okay. So let's say that this is, if this is less than P1 and P2, P2 and P3, P1 and P3. what is the largest probability of error that this will incur?
One
1 by 3, right? Why?
min of P1, P2, P3 is less than P1, less than P2, less than P3.
Correct.
Add them up.
Correct.
3 times min.
Yes. All right, so max probability of error is equal to 1/3. And when is this achieved?
All of them are 1 by 3.
All of them are 1 by 3, right? So there is a weak learner for this particular hypothesis class. But can you do better? In the sense, is it possible to achieve, is it possible to design a theta? In this case, I chose theta to be just one of these 3 values, right? Alpha or beta or 1. But let's say you're free to choose theta anywhere between 0 and 1. Can you achieve a worst case probability of error which is strictly less than 1/3? Why not?
Depends on, you could show it for each of the intervals. If you say theta is between 0 to alpha, you could
Correct.
choose.
Yeah, in each case, for every theta, alpha, and beta, you can show that there is at least one distribution which will achieve a probability of error at least 1/3. All right. So in fact, it's just using the base hypothesis class, doing ERM or anything on the base hypothesis class cannot achieve a probability of error that is arbitrarily small. So the base hypothesis class in itself cannot give you a strong learner. All right. So we need some way of, even if there was somehow I could combine weak learners, my final learning algorithm, or the final predictor that is output by the learning algorithm cannot be something from HB, right? Because I'm never going to be able to achieve a probability of error less than 1/3. Okay, so there are a number of other ways, the number of ways of aggregating these weak learners to produce a strong learner. One such approach is what is called bootstrap aggregation, or bootstrap aggregating. Also called boosting, also called bagging. So it comes from the name B AGG ING. And the high level idea is to somehow independently construct weak learners and take an average of these weak learners. So you're given S, the data set, construct IID samples, or IID, you're sort of going to resample from this data set to construct S1, S2, S3 up to Sk, each with a certain number of samples, let's say M samples each. Again, the samples from Si are coming from S, nothing else. You're uniformly sampling points with replacement from S. And for each Si, you are going to construct base classifiers H1b, H2b up to HKb. So these give you k different base classifiers. Hopefully each of these base classifiers is going to achieve a probability of error which is less than half, strictly less than half. All right, and then you take your H hat to be the majority of these. If there are more classifiers which predict a +1, then you output a +1. If there are more predictors that predict this to be the label to be -1, then you output -1.
So what are SIs here?
So basically you're taking this data set. From this, you are independently creating new data sets from this data set itself. Those are the SIs. So each SI consists of IID samples drawn with replacement from S. You're not getting new samples, you're just reusing the same data set multiple times.
So, but like the base hypothesis class is still same for all the weak learners.
Yes.
But the previous as you said, like if we work on the base hypothesis class, no learning algorithm can produce a strong learner.
Correct.
So like still, we're still not changing the base hypothesis class.
You're not changing the base hypothesis class, I agree.
Any learning algorithm produce a strong learner.
Um,
I thought like you'll be having independent weak learners, but with slightly different base hypothesis class.
No, we are always going to use the same base hypothesis class. But the point is that, okay, so here's a question for you. This H hat, right? Does this H hat belong to the base hypothesis class? Does it? Okay, let's just pick. I think I'm running out of time. So I'll leave this as a homework, but we'll pick this off the beginning of next class. But my suggestion is you take any three, let's say θ1, θ2, and θ3, different θ1, θ2, θ3. Those are your H1, H2, H3. And then see what is majority of H1, H2, H3.
All those SIs like pairwise inclusive,
Which one?
like all the SIs are like pairwise disjoint.
No, they're not.
They're basically
In fact, even within an SI, you could sample the same data point multiple times from S. That can also happen. Right? So right now, this is a heuristic method. Okay, and we are not going to really analyze bagging in much detail, but we'll use this as intuition to develop boosting. Okay, but the main thing is, again, I want you to think about it, is h hat for every h1, h2, h3, let's say, is h hat also in the Bayes hypothesis class or not? Okay, and what will happen if you increase the number of, if you increase k? Does it give us a richer class of classifiers? Okay, so let's stop here.